Now, this is where it's fully theory, so I will have to explain like in detail all of this with radiation. If you have any questions within radiation, please ask because this topic is a really, really big one. They ask this in every single exam, and they have really good theory questions that can be very difficult. Okay, radiation. What radiation essentially is when there's a nuclide that undergoes radioactive decay, it's going to emit radiation and to become more stable. Radiation usually can ionize atoms. So this means that if there's radiation somewhere and there's like these atoms floating around, these can call these atoms to become ions. Activity is what you would call the rate of radioactive decay, and they're measured in emissions per second or becquerels. I don't know how to pronounce that very well, but that is the unit. Remember the units very well. There are three main radiations I want to talk about, which is alpha, beta, and gamma. There is neutron, which is mentioned in some exam boards, but generally is not one of the biggest ones I want to mention. Neutron is very, is not too important, I would say. To detect this different types of radiation, this is not said on the slides, but to detect different types of radiation, there is these detectors called Geiger-Müller tubes, which help measure the radioactivity by counting the number of particles entering it. I'm gonna, hopefully you guys can see the chat, but I'm gonna type the name of this device out because that is Geiger-Müller tube. That is what you would use to detect the radioactivity, and this counts the number of particles basically entering it. So with the alpha, beta, and gamma, we'll just talk about that. Alpha particles, you can treat them as a helium atom. So 2 protons and 2 neutrons. They're basically the same structure. You can literally treat it as a helium. They have an atomic number of 2 and a mass number of 4. 2 protons, 2 neutrons. Beta particles, you can treat as a high-speed electron, an E-. So you would usually see a mass number of 0 and an atomic number of -1. It's technically not -1, but it's okay, yeah, you can't see the chat. There's something up with that. Okay, we'll type it out really quickly. There you go. Okay. Gamma rays, they are electromagnetic radiation emitted from the nucleus. And the neutron, as mentioned earlier, it is released from the nucleus as well. A neutron will essentially turn into a proton to release an electron. This is a bit wordy. I'm going to say that again. A neutron, so that's also considered a radiation, essentially. I will turn into a proton to release an electron. That's the best I can explain it. Okay, but it's not too important. Don't worry too much about neutron. I want you guys to focus more on alpha, beta, and gamma. So with alpha, beta, and gamma, let's look at the thing on the side in the corner, the diagram in the corner. The different radiations have different penetrating rates, and they have different ionizing power. Alpha, its range is very, very low. It cannot go past skin. It can't go past a piece of paper. It's not very penetrating. It's the least penetrating. Beta is slightly better. It can go through a few sheets of paper, a few sheets of aluminum foil, but it cannot go through lead. It's a bit stronger when it comes to penetrating than compared to alpha, but it's still not too strong. The strongest one would be gamma. Gamma is so extremely penetrating. It can penetrate thick sheets of lead and blocks of it. The one, not lead, it can aluminum. It can go through and penetrate lots of aluminum and lots of paper. However, because there are things that emit such strong gamma radiation, you would want to store it in these lead boxes. This is where really strong gamma radiation, radioactive material is put because it can't really go through lead. So again, alpha, least penetrating, beta, middle, gamma, most penetrating. Okay. Could you talk about motors and electromagnetism? Yes, I'll try and do that. Okay. With ionizing power, so I said radioactive material can ionize atoms, so they can form ions from these atoms. So alpha is the exact opposite of their penetrating. Alpha is so extremely ionizing. So alpha can turn atoms into ions very, very, very easily. And that's very dangerous. Beta, again, is just the middle, and gamma is the least. It does not ionize very well. It's not very ionizing. So why am I mentioning all of this? It's because there are two terms that you need to know about. I need to type this out. Irradiation, which is the first one, and contamination. Okay. Irradiation, contamination. Irradiation is when you were exposed to radiation. So it's not inside you, you're not ingested it, but you've exposed yourself to radioactive material. This is where gamma radiation is very, very scary because alpha radiation is not going to go through your skin. You're safe. Beta, a bit more dangerous. Gamma can go through some of your tissues because it's so penetrating. Therefore, that is when it's the most dangerous. Contamination is when you've taken in radiation. So when you've eaten something that has radioactive material on it, or you've accidentally drank something with radioactive material, that if it's in your body, it's extremely dangerous if you have alpha radiation. Because, as I said, alpha radiation is very, very ionizing. This can be so harmful to your body because it will ionize ionize the atoms in your body, breaking down your tissues. This is so bad for you. So it's good to know which is most penetrating and which is most ionizing because they sometimes ask questions on that. Okay. Within this topic, let me just quickly. We also talk about nuclear equations and half-lives. So with the nuclear equations, we have an example of going through this in a bit, but the nuclear equations, the nuclear equations, the alpha particles I said are treated as a helium atom. Geiger-Müller tube is what detects, it's a detection device detector that helps detect radioactive activity. Radioactivity. Sorry, don't know when that was. Bleh. Yeah, radioactive material. That's what a Geiger-Müller tube is. So, radioactive decay, they always give you these equations, try and figure this out. If it is an alpha particle, as I said, it's like helium. If it's a beta particle, it's like electrons, so you have a -1. And we will go through a question like that in a bit. Half-lives, very basic of half-lives you need to understand is that it's just the time it takes for half of the nuclei to decay in the radioisotopes. There is an equation of 1/2 to the power of n to figure out how much is left. This is again math. So if you want a bit more practice on half-lives and mathematical equations, please do have a look at that. The theory with half-lives that you need to know is that it is determined by the isotope of a nucleus. So the shorter the half-life, the faster an isotope will decay. And this is really unstable. So a longer half-life will be more stable. So a short half-life, the faster the isotope will decay, the more unstable it is. The question I want to look at is the second question here. It tells you this is the nuclear equations. So you can see the atomic number here is 36. You just need to basically do the math. You see that this is 0. 0 plus 85 is 85. So you're just going to have 85 here. Let me just type that out because I don't think that's horrible. Anyway, the bottom one, it's -1 plus something gives you 36. So we know that 37 minus 1 is going to be 36. So that's kind of the number we'll go with. I'm hoping this math makes sense, but this is just being careful with the top and the bottom numbers and being able to deduce what's the mass number and the atomic number. Bottom question, we're running out of time, so I don't want to go through this too much, but this is a really good question. So if you guys want to have work on radiation, 7.3, do this question. It's a very, very good question to do. It's a very good practice. And I have a feeling they might do this again this year, asking a similar question. So have a look at 7.3 if you have time.